Hi and welcome to another video in the probability series. This video covers the concept of mutually exclusive events. Two events are mutually exclusive if the occurrence of one rules out the occurrence of the other. Let's take a few examples. So here I have a table. I'm just going to look at this row of the table. Now this is an event here. It says James bought milk today. And here's another event. James didn't buy milk today. These two events are mutually exclusive. Why? Because if one occurs, the other can't occur. This event occurring rules out the occurrence of this event. If James buys milk today, then the statement James didn't buy milk today cannot be true. Let's move on to the next row. Here it says Jennifer won the lottery this year. The other statement says Jennifer didn't win the lottery this year. Now, if Jennifer won the lottery, this statement can't be true. You can't win the lottery and not win the lottery. So these two events are also mutually exclusive. Same thing with this case in the fourth row of the table, or this third case. Scoring a goal in a match is one event. Another event is not scoring a goal in the match. Now, if a player scores a goal in a match, the player cannot not score a goal in a match. So let me make sense of that. If the event that a player scores a goal takes place, then the event that the player didn't score cannot hold. So scoring a goal and not scoring a goal are mutually exclusive events. I mean, an easy way to just remember what mutually exclusive events are is just to think of the common saying, you can't eat your cake and have it. So if you have a cake, I'm going to make an attempt to sketch a cupcake. Just put some. So this is a cupcake. Well, it looks more like a house, but it's a cupcake with some icing. Let's have some icing. And say some cookies on the cake, or I don't know, some raisins, whatever you want to call all this. So that's a cupcake. Now imagine you have this delicious looking cupcake. If you eat the cake, you can't still have the cake because the cake is now in your stomach. So I mean, that's just a good way to remember. But just let's move on to more examples, more common examples, the examples you'll be tested on in terms of your exam, in terms of the questions you're going to see. So you know what a die is. You know, you have a cube essentially with numbered sides. So numbered sides from 1 to 6, where this single dot represents 1. You can have 2 dots on one side and 3 dots on another side. And on another side you have 4 dots, on another side you have 5 dots, on another side you have 6 dots. So this is just my own die. Imagine I have a die and I toss it in the air and let it land. There are how many outcomes? 6. Why are there 6 outcomes? Well, if I toss the die and it lands, I'm only considering what number I see on this top face when I toss the die and it lands. And there's 6 possibilities because there's 6 faces of the die. There's a face with a 1, there's a face with a 2, a 3, a 4, a 5, and a 6. So I have 6 possible outcomes. But what I'm trying to say or emphasize is that each of these outcomes are mutually exclusive. If one outcome is obtained, none of the other outcomes can also be obtained. So if you toss the die and it lands and you get a 1, you can't get a 2, you can't get a 3, you can't get a 4, you can't get a 5, you can't get a 6. So each of these outcomes are mutually exclusive. Once you get one of these results, none of these can take place. Moving on. What about a coin flip? Coin has 2 faces. One heads and the other tails. So I'm just gonna label this side heads and this other face is going to be tails. If you flip the coin, it will land eventually land, well, this is the assumption anyway, that's going to land flat on the floor and you're going to see a face. Let's say heads. Now there are only 2 possible outcomes. Either you get heads or you get tails. Now if you flip the coin and you get heads, so let's call the event, one event getting heads and the other event getting tails. Now, if this event occurs, this event will not occur. If this event occurs, this event will not occur because they're mutually exclusive. If you get heads, you can also get tails. If you get tails, you can also get heads because it's just one coin flip. By now, you should have an idea of what it means for two events to be mutually exclusive. If one event occurs, the other is ruled out. The other will not occur if they are mutually exclusive events. For the sake of perfecting your understanding of mutually exclusive events, let's look at the opposite. Let's look at non-mutually exclusive events. So events that are not mutually exclusive. Again, I have a table. Well, in this row, it says, James bought milk today. So that's an event. I'm calling this an event. James bought milk today. Another event is James bought mineral water. Now, these two events are not mutually exclusive because James can buy milk today and can also buy water. Buying milk does not rule out the possibility of buying water. Let's go to the second case. Jennifer won the lottery this year. Jennifer won the game show. Because Jennifer won the lottery does not mean she can't win the game show. So these two events can occur. One occurring does not rule out the possibility of the other, does not rule out the occurrence of the other. And it's the same thing here. If you score in the first half of a football match, it does not rule out the possibility or the occurrence of scoring in the second half of the match as well. So this table, each row of this table shows two events, or contains rather two events that are non-mutually exclusive or not mutually exclusive. So earlier we looked at the outcomes of tossing a single die. I noted that there are only 6 possible outcomes and they correspond to the 6 different numbers on the faces of the die. So you can get either a 1, 2, 3, 4, 5 or 6. So there are 6 possible outcomes, and once you toss the die and you look at the number you get, once you get a number, say you get 1, that means the other events or the other possible outcomes 2, 3, 4, 5 and 6 are ruled out. So outcomes of the toss of a single die are mutually exclusive. But now we're going to look at the outcomes of the toss of a pair of dice, so 2 dice. Now you can get from the first die, you can get a 1, 2, 3, 4, 5 and 6. From the second die, one can also get 1, 2, 3, 4, 5 and 6 as the outcome. Now, the possible outcomes of tossing the die are getting a 1 on the first die and getting any of these numbers on the second die. Getting a 2 on the first die and getting any of these numbers on the second die. Getting a 3 and any of these numbers and so on. Getting a 6 and any of these numbers on the second die. So there are more outcomes. In fact, there are 36 possible outcomes. I'm not going to list them all, but there are 36 possible outcomes. You can get 1 and any of these 6. So that's 6 possible outcomes. 2 and any of these. I'll rather not go into details so as not to complicate things at this early stage. But what I'm trying to stress is that the outcomes of tossing a pair of dice are not mutually exclusive. Because if I get on a 1 on the first die, it does not rule out the possibility of getting a 1 on the second die. If I get a 2 on the first die, it doesn't rule out the possibility of getting a 2 on the second die. So that's just all I want to stress. Also, if you look at coin flips, if I have 2 coins, so a pair of coins, if I flip the first coin, I can get either a heads or tails as a result. With the second coin, same thing, I can get heads or tails. Now, well, there are 4 possible outcomes. I can get heads with the first coin and tails in the second coin, or I can get heads on the first coin and heads in the second coin. Then I can get tails with the first coin and heads in the second coin, or tails on the first coin and tails in the second coin. So I'm going to summarize the results as follows. Heads with the first, heads with the second, heads with the first, tails on the second, tails on the first, heads on the second, tails on the first, tails on the second. So there are 4 possible outcomes from tossing two coins, flipping 2 coins rather. Now, getting a heads on the first coin does not rule out the possibility of getting heads on the second coin. Getting tails on the first coin does not rule out the possibility of getting tails on the second coin. So the outcomes of the two coins. So when you flip the two coins, the outcomes for each of the two coins are not mutually exclusive. You'll find out that in fact they are independent of each other. We're going to look at independent events shortly. But key thing I'm trying to stress here is that when you're flipping two coins or tossing a pair of dice, the outcomes on each of the dice or on each of the coins are not mutually exclusive. But when you're tossing just a single coin, tossing a single die, the outcomes on each die or on the coin, the outcomes are mutually exclusive, because once you get one, you can't get the other. Once you get one on one die, you can't get a 2, you can't get a 3, you can't get a 4, 5, or 6. Once you get heads on one of the coins, you can't get a tails. That's if you're flipping just one coin or one die. If you're flipping two coins or two dice, the result of the toss or flip of the die or the coin are not mutually exclusive. If you get heads on the first coin, you can also get heads on the second coin. If you get a 1 on the first die, you can also get a 1 on the second die. The events getting a 1 on the first die and getting a 1 on the second die are not mutually exclusive. The events getting a 2 on the first die and getting a 2 on the second die are not mutually exclusive. That's all I'm stressing here. So far, we've looked at the main focus of this video, mutually exclusive events. So if I have two events, A and B, and I tell you that these events are mutually exclusive, it means that the probability of event A, given that event B has occurred, is equal to 0. That's what this means. So P A given B. This means the probability of event A, given that event B has occurred. What I'm saying is, if two events are mutually exclusive, if event B has occurred, that means event A cannot occur. That's why the probability of event A, given that B has occurred, is equal to 0. That's the main idea of mutually exclusive events. Also, you can write it this way. The probability of event B, given that event A has occurred, is equal to 0 if event B and A are mutually exclusive. Remember, when the probability of an event is 0, that means that event will not occur. That means that event is impossible. And that's what I'm saying here. So imagine the probability of winning the lottery, given that you did not win the lottery, is also equal to 0. If I tell you that James did not win the lottery, what's the probability that James won the lottery? 0. And that's the main idea here. So now I'm looking at a coin flip and also a die toss. Imagine I give you a coin. It has two sides, heads and tails. Imagine I flip the coin for you and I then read off the name of the face of the coin facing me. So I read off whether it's heads or tails. Now, imagine I tell you that when I flip the coin, it landed such that I could see the tails end of the coin. What is the probability of getting heads, given that the result is actually tails? Also, what's the probability of getting tails, given that the result is actually heads? Well, the answer to these two questions is just 0. If I flip a coin and I get tails, that means the probability of getting heads is 0. It's impossible to get heads. If I flip a coin and I get heads, it's impossible to get tails. So the probability of getting tails, given that the result is heads, is obviously 0. So I'll just emphasize the meaning of this notation. The probability, well, this expression here is saying, what's the probability of getting heads, H? What's the probability of getting heads? But given that the result is tails, it's 0. What's the probability of getting tails, given that when I flip the coin, I got heads? It's 0. It's as simple as that. Also, with a die toss, a die has 6 sides, labeled with 1, 2. We're labeled from 1 to 6, so I'll just label the side with 3 dots. If I toss this die and I get a 1, I'm not going to ask you what's the probability of getting 2, given that I got a 1. The answer is obviously 0. What's the probability of getting 2, given that I got a 2? Obviously that's 1, because that's certain. What's the probability of getting a 3 given that we got a 1? It's 0. What's the probability of getting a 5 given that we got a 1? It's 0. This all makes sense because in a die toss, there are only 6 possible outcomes and you can only get 1. If I tell you that the result of the die toss is 2, then the probability of getting a 1, given that the result is actually 2, is 0, because you can't get 2 and get 1 as well. Once you get 2, then getting 1 is impossible. That's all this expression means. So that's the main idea of mutually exclusive events. Now we're going to look at the addition of probabilities for mutually exclusive events. Now, if two events, A and B, are mutually exclusive, the probability of event A or event B occurring is equal to the probability of event A occurring plus the probability of event B occurring. It's as simple as that. So I'm going to go through this example to demonstrate this rule. So this is something you have to remember. So we have a fair-sided die and we toss it. So we just have one die, we toss it. And the question says, what is the probability of obtaining a 3? What's the probability of obtaining a 4 or a 3? And what's the probability of obtaining a 2, 3, or a 5? So when you toss a die, what are the possible events or outcomes? Well, the possibilities are getting a 1, getting a 2, getting a 3, getting a 4, getting a 5, or getting a 6. So the first question says, what's the probability of getting a 3? Remember from the video on theoretical probability, probability of an event occurring is the number of ways that event can occur divided by the number of possible outcomes. Number of possible outcomes. Now, in how many ways can you get a 3? Just one way. And how many possible outcomes are there? There are 6. So the probability of getting a 3 is 1 over 6. The second question asks for the probability of obtaining a 4 or a 3. So it says, what's the probability of getting a 4 or a 3? Well, from this formula, the probability of getting a 4 or a 3 is the probability of getting a 4 plus the probability of getting a 3. What's the probability of getting a 4? It's the number of ways you can get a 4 divided by the number of possible outcomes. And how many ways can you get a 4? So this is the sample space, basically 1, 2, 3, 4, 5, and 6. This is sample space for the event of a die toss. And these are the possible outcomes. How many ways can you get a 4? Just one way. And how many possible outcomes are there? There's 1, 2, 3, 4, 5, 6. So 6 possible ways. So the probability of getting a 4 is 1 over 6 as well. So the probability of getting a 4 or a 3 is equal to the probability of getting a 4, which is 1 over 6, plus the probability of getting a 3, which is also 1 over 6. 1 over 6 plus 1 over 6 is 2 over 6, which is equal to 1 over 3. And the final question asks, what's the probability of obtaining a 2, 3, or 5? Now, the probability of getting a 2, or 3, or a 5, according to the formula, is equal to the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 5. And that's equal to what? What's the probability of getting a 2? It's the same as any of these. The probability of getting a 2 is 1 over 6 because there's only one way you can get a 2 out of 6 possible outcomes. Probability of getting a 3, we already determined that to be 1 over 6. The probability of getting a 5 is also 1 over 6 because there's only one way you can get a 5. Only one way you can get a 5 out of 6 possible outcomes. So the probability of getting a 2 or 3 or 5 is equal to 1 over 6 plus 1 over 6 plus 1 over 6, which is 3 over 6, which is equal to 1 over 2, which I can write as a decimal as 0.5, or in percentage form, I can write as 50%. Remember, when you're converting a probability on a linear scale to a percentage scale, all you have to do is multiply by 100 and append the percentage symbol. Now, this equation you see here applies only to mutually exclusive events. So I'll just add an extra one. the probability of event A or event B or event C occurring is equal to the probability of A plus the probability of event B plus the probability of event C. It only applies to mutually exclusive events. In this example here, we actually use this equation. Why? Because the outcomes of a die toss are mutually exclusive. Once you get a 3, you can get a 2, you can get a 1, you can get a 4, you can get a 5, you can get a 6. Once you get any of the outcomes, all the others are ruled out. Hence why this equation applies. So you have to look out for mutually exclusive events and know which formula applies to them, because shortly we're going to look at a dependent event and a different formula applies. So you have to be careful. Notice that this is a case where a single die is tossed.